Hey there, my name's Mitch,
And my name's Tom.
and we're with FAMU FSU College of Engineering, and we performed a couple experiments on the Keysight RF Microwave Kit. We tested the transmission line and the RF filter components passively, but now I'll pass it on to Tom to give us a little bit of the background on the theory.
Yeah. So as we say, the first part is the transmission line, which is the most fundamental components of the RF engineering, and it can construct various the structure of the RF circuit, which can manipulate the RF signal and realize the function we want. So two key parameters for the transmission line. One is the Z naught, which is the characteristic impedance. Another one is the beta L, we call it electrical length. And switch to the RF filter. We know the filter is always filtering the spectrum range we want, which can make our RF system can operate at a certain range of the frequency. So now, Mitch, would you want to let us know what is the key parameters we want to measure for both the transmission line and the filters?
So for the transmission line, the key parameter that we're measuring is the S parameter, which is a complex number that is derived from the magnitude and the phase of the system. Switching over to the RF filter, the key parameters that we're measuring for that is the S parameters and the stop and pass band. Stop and pass band will allow us to know at what frequency the filter operates at and what frequencies it will allow to pass through the system. And finally, for the RF filters, we're also going to be measuring the group delay. But now we'll go into the experiment that Tom will conduct.
Okay, now we see that we have produced a setup for a connection of our filter. This filter is the lumped element based filter, where the components have exactly the same value with the simulation we conducted. So you see there's three capacitors and the two very large size of the inductors. Then we can check out our measurement data to compare with our simulation.
So here we see some of the passive components in our experiment that we built on ADS using inductors and capacitors. After we finalized our experiment and extract our experimental data, we overlaid it with the simulation. And the next slide shows the overlay of the simulation and the experimental data. The simulation fit very well with the experimental data, as you can, and we labeled the center frequency and the stop band of both the experiment and the simulation, and they were seen to be the same. Next slide shows the phase graph, and as you can see, they have good congruency. So here shows the parameters, and our simulation represents the most ideal scenario, and so because our experimental measurement or experimental data is very close or estimated to be very close based off what we found or what we extracted from the data, which were the stop frequency, pass band, center frequency, and group delay, which shows that our experiment had a good agreement with our simulation. Now we'll go into our transmission line simulation and experiment.
Then this time we're gonna check the transmission line. So there are several transmission lines. We're gonna pick one of these to do the measurement.
One question I have for you, Tom, is what's the width of our transmission line sample that we're using?
So it does have the three different versions of the transmission line. So the only difference is the width of the transmission line. So on the top we got 17 mils, and in the middle is the 14 mils, and the third one, the bottom one, is the 25 mils. So the different the change of the width of the transmission line will really affect the characteristic impedance Z naught of the lines. If the Z naught has changed, it will lead to the impedance mismatching to your port impedance. That will change the performance of your result, like you basically change the magnitude, the insertion loss, and the return loss. So that is mainly the difference. So for this time, we're gonna just pick the 17 mils to do the measurement and see how it works.
Alright, for this diagram comparing the phase response of the simulation and the experiment, we see that it has good agreement, and picking a point at 1 gigahertz, we see that the phase is around 57 degrees. And the next slide shows the overlay of some of the S parameters that we extracted from both the experimental and simulation data. And here shows the parameters of the transmission line simulation and experiment. As we see, the return loss has a great difference, which could be attributed to discontinuity at the ports. And however, the max insertion loss, the phase at 1 gigahertz, and the group delays all show similar values, which shows that our simulation was a good predictor of our experiment, and our experiment had good agreement with our simulation.